Hi, in this video we'll look at entropy and information gain. So another error metric that we can use to decide our splits, indices and trees is entropy. So entropy is defined as follows. Let Pi is the probability of occurring or obtaining a point of class I. And Pi is defined for all the classes, and let's say we have k classes from I belonging to 1 to k. Then the entropy is defined as sigma pi into log on base 2 of 1 by pi, where I is equal to from 1 to k. So we can choose the split which minimizes this entropy, and to better understand this entropy measures the average information content. So this is called as information content and expected information content. Let me denote this by information content by class I. So expected information content is probability of obtaining class I multiplied by information content of class I, and we sum it for all I is equal to 1 to k. So now let's understand why we call this as information content. Now to understand that, let's say ith item appears x times, which means, so let's say if we had n different items, number of bits required to differentiate between these n different items is log n on base 2. But we know that out of these n different items, x items are same, and number of bits required to distinguish between those x items is log x on base 2. And by number of bits means, like let's say we had 4 items, so log 4 on base 2 is basically 2. So basically we require 2 bits to distinguish between 4 items, and so basically those 4 items can be differently assigned one of these bits, and that's why 4 items can be differentiated only using 2 bits. So now since all of these x items represent the same class I, so instead of representing class I with log n bits, we can represent class I with log n minus log x bits. So basically what it means is that, let's say we had 0 or 1 log n bits, using which we could recognize class I, but let's say if we change x bits, let's say some x bits of this, if we change the x bits, let's say we make it 1, we keep it to be 0, we make it 0, we take it 0. So if we change the x bits, the class does not change. So basically the common thing between every item of class I is the remaining log x bits. The class does not change. If we change the log x bits, the class does not change. So basically, irrespective of the log x bits, the class remains same, and which is the class I. So we can represent the class I using, so what matters is log n minus log x bits. The remaining bits decide whether it's class I or not. So for a small example, we can say, let's say we have 3 items, and 2 of those items are A, B and C. So ideally, if there were 4 different items, then we could assign each one of this to the 4 different items: item 1, item 2, item 3, item 4. But since we have only 3 different items, what we can do is we can assign item A to this, item A to this, item B to this, item C to this. So what we can say is that instead of using 2 bits for item A, don't use 2 bits for item A, use just 1 bit, which is, so probability of A is 1 by 2, x is 2, n is 4. Log base 2 4 minus log of base 2 2 is 2 minus 1, which is 1. So basically we can say that if our bit is 0, so this is the log x bits, which does not matter. Whenever the bit is 0, we won't look further. So the number of bits required to know about A is 1. But to know about B, we need 2 bits, because just 1 does not say anything. It can be B also and C also. So we need to know 1 and 0 both to know about B. Similarly, to know about C, we need we need to know both the first one and the second one. So if item is repeated X times, what we will do is we will just look at the first log n minus log x bits, and rest of the bits won't matter. We don't need those bits to identify that this is the ith item, and hence the amount of useful information the ith item holds is basically log n minus log x, which is log of n by x. So basically, if a group has more number of items, then we would require more number of bits to represent that group, and hence we will say that that particular group contains more information. On the other hand, if a group contains more similar items and less distinct items, which means we have less information in that group because we need less number of bits to represent that group, and hence we will say that the group has less information. So this is the idea, and log n by x is nothing but log of 1 by pi. So this represents the amount of information contributed by the ith item. So 1 by pi represents amount of information contributed by ith item. But this information appears only with the probability pi. Hence the expected number of bits required. So entropy is nothing but expected number of bits required to represent the items in a set, because log of 1 by pi represents the amount of information. Amount of information means number of bits required to represent the ith item, and entropy represents expected number of bits required to represent the entire set of items. And if items contain if the set contains more number of different items, it means the set has more information. But the goal of decision trees is that the set should be more homogeneous, and hence we have to minimize the entropy, which means we want the items in a particular set to be more and more similar. And that's why it is one of the error functions that we can use for our decision trees. So in this example here, we have let this region be R. In the region R, we have 5 blue dots and 5 red dots. So probability of blue is 1 by 2, probability of red is 1 by 2. Therefore entropy of set R, region R, is 1 by 2 log of 2 plus 1 by 2 log of 2. This is equal to 1 by 2 plus 1 by 2, which is equal to 1. Now let's say we divide the region R into two parts, R1 and R2, like this. So the entropy of region R1 can be calculated by saying probability of blue is 4 by 6, which is 2 by 3. Probability of red is 2 by 6, which is 1 by 3. So entropy of region 1 is minus 2 by 3. So we can write this as sigma I is equal to 1 to k minus pi log of pi. So entropy of region 1 is minus 2 by 3 log of 2 by 3 minus 1 by 3 log of 1 by 3. And similarly, entropy of R2 is probability of blue for region R2 is 1 by 4. Probability of red for region R2 is 3 by 4. So entropy of R2 is minus 1 by 4 log of 1 by 4 minus 3 by 4 log of 3 by 4. So to expand further, entropy of region R1 is 2 by 3 times log of 3 minus log of 2 plus 1 by 3 times log of 3 minus log of 1, which is equal to log of 3 minus 2 by 3 times log of 2, which is equal to log of 3 minus 2 by 3, and log of 3 on base 2 is 1.584 minus 0.66, and this is equal to 0.924. And entropy of region 2 can be written as 1 by 4 times log of 4 plus 3 by 4 times log of 4 minus log of 3. So this means log of 4 minus 3 by 4 times log of 3, which is equal to 2 minus 3 by 4 times log of 3 we just saw is 1.584. So this is equal to 2 minus 1.18, which is equal to 0.82. So now we know that the region 1 contains 6 out of 10 data points and region 2 contains 4 out of 10 data points. So to calculate the final entropy, so entropy after split on feature x1 is 6 by 10 into 0.924 plus 4 by 10 into 0.82, which is equal to 5.544 plus 3.28 by 10, which is equal to 0.88. So entropy is reduced from 1 to 0.88 after the split. So initially the entropy of region R1 was 1 and entropy of region R1 plus R2, weighted entropy of region R1 plus R2 after the split is 0.88. So now I hope entropy is clear to you. So now we look at information gain. So information gain is nothing but reduction in the entropy. So in our case, information gain by splitting on feature x1 is 1 minus 0.88, which is equal to 0.12. Now let's consider the case that we have total n items and we have total k classes, and probability of each class, where I is a given class. So probability of each class is equal, and let's say probability of, since there are k classes, probability of each class is equal to 1 by k. Then entropy would be, since there are n items, so sigma pi log of pi I is equal to 1 to k minus sigma I is equal to 1 to k, since we have k classes, so pi is equal to 1 by k, and log of pi is log of 1 by k. So this would be equal to minus log 1 by k. This will be equal to log of k on base 2. So if we have k classes, the maximum value entropy can take is log of k base 2. And this is quite evident because since we have k classes, the maximum number of bits required to represent k different items is log of k on base 2. So let's consider a special case where we have only two classes, k is equal to 2. So we know that now we have only two probabilities, p1 and p2, and we know that p1 plus p2 is equal to 1. So p1 is belonging to the class 1, p2 is the probability of belonging to class 2. So our entropy formula becomes p1 log of p1 minus p2 log of p2, and basically this would become minus p1 log of p1 minus 1 minus p1 into log of 1 minus p1. So if we if you plot this entropy, so this is entropy, and the maximum value would be log of 2 on base 2, which is 1 in this case. In general, the maximum value of entropy can be log of k on base 2 if we have k classes. So the graph would be something like this. The maximum value would be obtained when p1 is equal to half. So if p1 is equal to half, entropy is 1 in case of 2 classes. In case of k classes, when probability of each class is 1 by k, then we achieve the maximum. And in case of 2 classes, if the, let's say, probability of first class is 0, then we'll get minus p1 is 0, minus 0 log 0. Log 0 is infinity, but by definition we define this product to be 0. 0 into infinity we define to be 0, minus 1 log 1. So log 1 is again 0, so overall thing becomes 0. So at these extreme points, the curve is 0, and it is maximum when p is equal to half. So I hope entropy and information gain is clear to you, and I hope you like this video. See you in next video.